Welcome to section 2 of the materials topic. This is all about Hooke's law. Robert Hooke, who is a great researcher and scientist in all kinds of ways, whose theories of gases and behaviour in gases was based on his discoveries on springs. He's also the first person to write books such as Micrographia, which was the first popular science book ever. Lots and lots of things you could see through a microscope that had just been invented, all kinds of stuff. Anyway, so we're going to look at Hooke's law itself and then expand that into different systems so you can start to get to the level where you're considering multiple spring systems.
Okay guys, here's a little bit of introduction to this section of chapter 2. I'm actually not going to do the whole thing, just this lead up into the practical that I want you to use so that you can start to get a bit more development with the skills. There is a bigger version of this practical that we're going to do called Young's modulus. Similar idea to Hooke's law but not the same, so we're going to use this as a bit of practice. Okay. Just to be clear, Hooke's law, we normally think about extending springs. So these are what we call tensile forces. We're stretching something. The two forces are outwards. So here's our object, and our forces are in that direction. However, it's just as valid when we're talking about pressure or compressive forces. So compressive forces are where you are compressing and pushing inwards. Okay, it doesn't matter what you're doing with it. In the end, these two forces will always be the same. So if you try and push harder at one end, it will just move sideways until they're the same size, and then it starts crushing. Likewise here, stretch, you will have the same force all the way through. So that tensile force is uniform all the way through the material. So Hooke's law, now it might seem a bit odd, is obviously for a spring because you've learned that at GCSE, but actually if you take a material, commonly a metal wire, and you hang it, then actually that will be stretchable. Okay, it will have tensile properties, you'll be able to stretch it. Some materials stretch a really small amount, some stretch a tiny amount and then break and so are brittle. Some are what we call ductile and they're quite stretchy and they thin out, so that's often how they make metal wires. And then some materials won't obey Hooke's law at all. Things like natural rubber, for example, that's very stretchy, but it just doesn't obey the mathematics. So key bit for this, say a little bit of information, but if the extension increases linearly, so that gives you a linear graph, then that is Hooke's law. It must be under Hooke's law. So what Hooke's law actually states is that the force needed to stretch a spring, because he was talking about springs, he also analysed other materials like gases and he used them based on this model of springs, and they're actually very good explanations. But yeah, to stretch the spring, this force is directly proportional to the extension of the spring. Okay, so not the length, it's the extension that matters. So he did add a little bit more, and that's really, really important. Okay, but we'll come back to that one because we'll just go with the ideal at the moment. So, simple idea, I tend to think about doubling with stuff like this. So in the spring, if there is twice as much force, it's going to stretch twice as far. Okay, half the force, half as far extension. Okay, but again, it's extension, not length. So X for this, extension, F, force, and basically that's a proportionality. It doesn't give us an equation, so to get an equation we will need to multiply it by a constant. That constant is only as long as they are proportional, which he discovered they were. So that multiplying factor actually comes from experimentation, but in terms of definition, yeah, it's the force required per unit extension. So force divided by X will give you K. So great, nice and clear. I think it's quite a nice easy way of thinking about it. K is going to have units of newtons per meter, so how many newtons to stretch each meter, but you may want to think of it as stiffness, and they will tend to talk about that quite a lot. So if it's a stiff spring, it's quite hard to stretch or compress. And if you do that in the experiment that I want you to do and you plot it, what you'll get is a graph that looks like this. Now normally we'll put the extension, the independent variable along the bottom. We're going to do that here, but it means thinking about it in a slightly different way. So I'm going to put the extension here. It will make the maths easier to do with your graph. But the way to think about it is, if we actually extend a spring, what it will do is it will pull back against your hands. The size of the force exerted by the spring depends on the extension. Obviously the extension depends on how hard you pull on the spring. So you could put the graph the other way around, but basically we can work with force up the side, extension along the bottom, and that's perfectly valid. Okay, so if we arrange Hooke's law, we get to one of the fundamental skills of physics practicals. We use data, ideally a lovely linear graph, to give us an equation. And what you should find with your graphs is it will go through the origin, 0, 0. And what that means is we can fit it to a y equals mx plus c graph. Okay, how do we find gradient? Well, if we just take that mx plus c, okay, and I'm going to put that in brackets because that equals 0, then if we take what was on the y-axis and divide it by x-axis, we'll get the gradient. So effectively, if we take the force and divide it by the x, which is extension, force over extension, we will get a value, and from our definition here, that value is going to be k. Okay, so in your experiment, I want you to plot this for a single spring, for two springs in parallel, for two springs in series, and what you'll find is you get two lines either side of the single one. Excuse me. And by finding the gradient, what you'll find is the change in force, change in extension, and if you divide one by the other one, what you'll get is the value for spring constant. And if you use that in meters and that in newtons, then it will be in the correct unit, because it will be newtons divided by meters, newtons per meter. Okay, so that's enough to get you going with the experiment. It does link in with the chapter I've not given you yet on purpose. So what that does is we can start thinking mathematically what that means, but far better is if we can think about what happens to the extension when you put a force on it. Okay, leave it there, and now go away and do the practical, and you'll find the values from the graph. Practicing getting values from graphs, gradients from graphs, is really important in physics. We do it.
So what we're going to do is start looking at systems of springs based on this same idea. So keep in your mind, rather than get bogged down in the maths, keep in your minds that K is the stiffness, this value of force per unit extension. So how much force it needs to extend it. So what we can do is start thinking about these different spring setups where K is our normal spring, okay? Then we start to put them into different combinations, we get different behaviours. So in this one here, although it is already long, what we're doing is we're putting the same force pulling on both springs. So we're actually extending each one by the same amount, so this one has a much larger extension, because it's basically got the same force acting through each spring. So each spring extends by the same amount. This one, what we're getting here is effectively you're getting that split down the middle. So you're basically getting half of the force on each side, yeah? Half F. And so because you're getting half of the force on each spring, then what you'll get is half of the extension. So smaller extension. So effectively what we're doing is that when you put springs in parallel, you're making them stiffer and stiffer. They're not extending as much, or think of it as you need much more force to stretch them. So in a car, for example, you've got 4 wheels, 4 springs, you'd need 4 times as much force to make it squash down as much. Okay? Or for the same load, it presses down less. So this one again, there's a different way of thinking about it. You can throw it on its head in that you don't need as much force to stretch it the same amount as a single one. I tend to think of it as you get a much larger stretch when you get a much larger length of spring. This links that into strain that we're going to get into in the next section of the chapter. So in terms of just treating it mathematically, when we have it in series, when we are connecting them together, okay, what we're actually getting is an equation that looks very similar to resistors in parallel. So you might want to think of it like that. Makes it a little bit easier to get your head around. If both are springs, and again this at A level is what you will get, if they're both the same, then what we've got is 1 over the total stiffness, or spring constant, is going to be 1 over k plus 1 over k, which means that you're obviously going to get 2 over k to give your total. So if we turn that upside down, then kt equals half of the original k, okay, where k is your spring here, single spring on its own. So basically it's half as stiff. It is, shall we say, more floppy, more stretchy than a stiff spring. Okay, it's stretchier. If you put them side by side, then like old-fashioned chest expanders, the more springs you add, the harder it is to pull it, and therefore it makes you that bit stronger. So what we've got in here is that if we put them together, then our total spring is going to be, again, for A level, k plus k, which doesn't make a genius to realise that the total is now twice as big as the original. Okay, so it's twice as stiff. Be careful when you're doing questions like this that you don't just say it's longer or smaller, it's how much smaller and how much longer. Okay, so if you've got 2 springs that are the same in parallel, it will be twice as stiff. K is twice as big. If it's 3 springs, it's 3 times as big. 4 springs, 4 times as big. Okay, so get your numbers in there, makes it much, much easier. Now, there's a little bit here which does link back to the graph that we've just had. And the graph itself is very clear when you start thinking about this, because if we look at that, if I can turn it over, what we've got here is a force times extension graph. Now, that's basically the distance we're stretching it, the displacement that we're adding to it. So we've got force multiplied displacement if you have the area, which means that if you're taking that, not the gradient, which is to get k, but the area underneath, you're actually finding how much energy you have put into this, stored up in the spring, because that is equal to the work done, force times displacement, stretching it. So when you do work, you are increasing the energy inside the system. Okay, so that work changes into that internal energy, okay, the strain energy. You may have called it elastic energy, but we'll get into calling it strain, and again you'll see why in the next section. Okay, so strain energy is better. If you do that, then what you'll find is it's not just the force and not just the extension, because from what we've just covered above and overleaf, the more you extend it, the bigger the force. So actually what we're after is we are after the average force. Okay, and because it's a nice linear graph, it's a nice straight line graph, the average force is half of the maximum. Mathematically is the second reading, the maximum, subtract the original reading, which is 0, and divided by 2. So it's half of the maximum force. And if we put those two together, then we simply get the idea that energy stored up inside, I'm going to call it strain energy, there, half Fx. Okay, so it's half of a square, that is F, multiplied by x. Does it link back to the graph? Well, yeah, obviously, because if you take that maximum force, which is F, and you have your displacement, which is maximum displacement x, F times x will give you a square, you want half that square. Okay, so although the actual reason is because we're finding the average force, what you're doing is effectively finding the area under the graph. So the graph makes it much easier to do. Unfortunately, you don't always know the force. Okay, what you do know and what you can measure very easily is the extension. So if we know about the spring or the spring combination, then we will have a value for K and we will have X. So if we put that in, then we get a far more useful version. So if we use F equals Kx, okay, and we put it into our equation, then what we've got is our strain is going to be half Kx for F, so replacing F with that equation there to get Kx, multiplied by X, so it doesn't take a genius again to work out that that is half Kx squared. That is by far the most useful equation, okay, because you know about the spring and you know how far it's stretching. Okay, so really, really useful. Remember it's squared. Don't muck up the maths by doing that. Now, there's a little experiment you can do which is very interesting, in that lots of materials do not obey Hooke's law. Okay, so this, for example, is a polymorphic type of graph, a material that is polymorphic, such as rubber bands. So here's a little thing for you to try at home, nice and straightforward. Your lips are quite sensitive to temperature, so get an elastic band and hold it against your lips, and then do lots of work. When you stretch it and then relax it, what will happen is it doesn't relax in the same way that it does with stretching. So what you'll find is it's quite stiff to start with, and then the longer it gets, the less stiff it is, the less force you need to make it stretch that extra bit. Whereas at the end, what it does is the force disappears very quickly, and then the last bit it kind of goes stiffer again. So what you'll find is the changing properties of the elastic band mean that instead of a straight line graph, it's got a curve, and the curve going and coming back to its original length, so its original extension of 0, you'll get a difference. What that means is, if we think about the area and therefore the energy it takes that you need to add, the amount of work you need to do to stretch it, is more than it gives back when you let it go. This bit is internal energy. So it's the energy that's left, let's say, stored inside. So that energy ends up in the elastic band. So if you get an elastic band and then stretch it a lot, okay, and then hold it against your lips, you'll feel that it is a lot hotter. Okay, there's a big measurable difference of energy, and this happens everywhere that you're stretching and relaxing, sorry, wrong way around, stretching and relaxing non-metallic substances, including planets. Io is an incredibly volcanic moon of Jupiter, and the reason it's so volcanic is it stretches and squashes under the gravitational field. And because of that, you end up actually storing up energy inside it enough to melt rocks and therefore make volcanoes within the moon itself. So yeah, this hysteresis, this gap in energy, okay, is a way of putting energy into something and storing it inside. So yeah, try it with an elastic band. It'll work brilliantly. It will not work with a carefully done, really slowly and gently, carefully done stretching a metal, okay, which is what we're going to get into at the end of the chapter. So it won't do with that, it won't heat it up, but if you do something like an elastic band, you will. Try it, you'll be impressed. Right, we'll move on to stress and strain, because this links into this, but it also links into these ideas, and it links into this kind of idea here. Okay, we'll leave it there for today.